Okay, so we are going to go through the 2016 test, and we are going to go through selected questions because we are only looking at assessing you for Chapter 1. So just take note, though, of the formula sheet. This is what you'll be given. Okay, a couple of those things are not from Chapter 1. So, for example, this one here and this guy here. So I'm pretty sure, and we probably don't even really need power as energy over time, but because that also relates to the stuff from Chapter 2.1. You'll have to use the specific heat capacity tables which have been given to you. Same thing for the latent heat and also the latent heat of vaporization. So we can only give you those elements, or like in the case of water, please make sure that you are using for the different latent heat for fusion for water as a liquid as well as vaporization. So let's get started. Convection takes place. Now you can answer this one. What's the answer? Liquids and gases, yes. So liquids and gases is the transfer of heat, energy, but it's only in liquids and gases. And now a thermos flask have a silver layer on its thin glass walls to reduce energy loss by, Gary, do you reckon you could have a go at this? Well, would it be convection, do you think? Would convection have anything to do with a silver layer of glass? Yes, radiation is correct. So reading the question, now, generally speaking, well, the thermos layer, what it does is it keeps that heat energy in by reflecting it back, if you like. Okay, so that's sort of like what we're talking about, the silver blanket. In that heat energy doesn't, less of that it's going to escape. It sort of rebounds off that shiny surface. Now, your bicycle has been left out in the cold and frosty night, and in the morning you ride to school. The rubber handle grips do not feel as cold as the metal handlebars because, well, the metal is a better conductor of heat than rubber. So it's certainly not the rubber has a higher heat capacity than the metal, okay, because it would actually probably have a lower heat capacity. The metal is a better absorber than a rubber. That's just there to distract. And the metal is a better radiator of heat. No, that doesn't make sense either. Now, car radiators are likely to be painted. Now, you're the car man, Giuseppe. What colour do you think a car radiator would be? Would it be black or white?
I'm going to say white.
No.
If they're trying to get rid of heat.
Well, yeah, but black emits heat more readily. So if you've got your black and then your matte substance, so black is actually going to emit more heat. So do you want heat in the radiator? You want heat away from the radiator. Yeah? So it's black, so they emit heat readily. Okay, now of the listed below, which of the former, we didn't go through electromagnetic radiation. That was from section 2.1, so I can just get you to cross that off. Same thing with the surface area. Now, that was also, now what happens, and we discussed this, as you get out of a pool and feel cold in the wind, what's actually happening? Like you're basically getting this water which is evaporating, and then that evaporation, you've got evaporating, and then what that must mean that you know how you get out of the water and you might feel cool in places? Yeah, and that's due to that fact that it's evaporating, it's increasing heat, I guess, but that's a decrease of thermal equilibrium, I guess. That's a decrease in heat on your body. So the type of heat transfer, it's actually just evaporation. Remember, you've got to pick one which is the closest. Okay, so, well, because it's not. Radiation is a transfer of heat, like for example, like the sun. But so in actual fact, you are feeling cooler due to the evaporation of the water as you get out. Now, what main mechanism of heat transfer occurs when the classroom door is left open on a cold day? Nikita? Convection it is. Yeah, so when you start thinking about wind and currents and things, then we're thinking convection. Air is a gas. And what main mechanism of heat occurs when you sit on a cold stone bench? Hanako? Conduction it is, very good. And when I'll accept two things for this. When pie's baked in an oven, it's by two things. First of all, we're looking at radiation. Okay, so radiation, absolutely, like your convection ovens are certainly using radiation, but I'd also use convection as well, not conduction. No, conduction is when the two things are in contact. Okay, you might have a pie sitting in, or think about like halfway through a chicken pie or something like that. That's not in contact with these things. So yeah, convection and radiation. So we'll move on to the short answer section, and look, I'm pretty sure you can do most of these basic calculations, but how much heat energy? So at the moment we're thinking heat energy, we're thinking Q. Does an electric jug need to transfer 1750 mils of water? So what we're going to do is we're going to convert that mass. That's 1.75 kilograms. Okay, so we've got to be in kilograms. 1750. There's no point writing 1750 out. And to raise it from 14 to 90 degrees. So that change in temperature is equal to 90 minus 14, which is 76. And assume that the heat process is 100% efficient. So we're looking at water, so we've got to use the heat capacity of water in joules per kilogram, which is 4,200, is it? Liquid water, 4,200 it is, yes. So we're going to do that times 4,200 times 76. And what that's going to give us is 558,600. Now, you don't need to write that out. What we could do is we could do that and into scientific notation to maybe a couple of decimal places. Okay, a big number like that. So what I'm going to do is I'm going to say, okay, let's go back 1, 2, 3, 4, 5, and let's round that 8 up to 9. Okay, so let's do 5.59 by 10 to the power of 5 joules. And that is perfectly acceptable. Similar, we've got water again. This time our mass is 150 grams. Ooh, don't know what happened there. 150 grams is 0.15 kilograms. And it received 16,000 joules of energy. So 16,000 is Q. What temperature must it reach if its initial temperature was 15 degrees? So we want to find the change in temperature. Remember the change in temperature, how much it changes. So we'll need to take into consideration that it's raised a certain temperature, and then we have to add that temperature to 15. So C is 4,200. So let's write out what we know. We've got 16,000 is equal to 0.15 times the specific heat capacity of water times the change in temperature. Now, the change in temperature is, so that's going to be the change in temperature, rearrange that, use your calculator. So we've got 16,000 and we're dividing both sides by 0.15 times 4,200. Now, when you do that, that will give you around about 25.4 degrees. So the final temperature is 15 plus 25.4 degrees, which is 40.4 degrees. It'd be a shame to do all that hard work and stop there. You'd only get 1 mark. You wouldn't get the answer mark. Okay, so not so bad, I hope. Is there any questions so far? Now, let me just briefly talk about the next question, which is a calorimeter. It's used to decrease heat loss in a number of ways, and I want you to mention, well, what ways would we be mentioning? We'd first of all talk about one which would be conduction. So all the surfaces have an insulative layer. So there are different layers. So that's going to reduce conduction. Convection. If we have a tight seal, then we'll have less heat lost at the top. Okay, because of that. I guess the less air getting in and out. And the last one, as we talked about in the multiple choice, would be radiation. So during a physics experiment, so it's an insulated vessel, so that insulation would definitely reduce heat loss by conduction. So prevented by the insulative layer. Radiation, the shiny surface, reduces heat loss. And convection. So a tight seal to prevent loss through convection. There's no doubt that when you're doing your test, you need to come up with some examples of conduction, convection, and radiation, heat loss, and heat transfer. Now, this thing about the star, can I please get, you probably already got it crossed. None of that we need to do. However, this is definitely a question that you could get. Describe what happens when two objects at different temperatures are placed in contact with each other. Make reference to the kinetic theory of matter and the law of thermodynamics. So what we can say is that heat transfer, does it happen from colder to hotter objects or hotter to colder? Yes, so heat transfer occurs from hot to cold objects until they reach the same temperature. Until they reach the same temperature. And I guess by mentioning that's thermal equilibrium. Now this is the zero law. The zero law of thermodynamics. Now, what does kinetic particle theory suggest? So the kinetic particle theory, we've got 4 marks. So we've probably got 2 marks for getting close to that. Or probably even 3 marks. Basically, what it's saying is that hotter, faster particles transfer their kinetic energy, their kinetic energy to nearby slower particles. So yeah, look, that's probably mentioning thermal equilibrium and heat transfer from cold, and then mentioning that it's a 0 law of thermodynamics and kinetic particle theory. That would give you your 4 marks. So hotter, faster particles transfer their kinetic energy to nearby slower particles. Now, it's partially discussed in radiation, but it's really sort of continues on in chapter 2.1. State 4 factors that influence the emissivity of a given surface. Is that crossed out, or is that? Yeah. It is. Yeah. Some of those things, though, are things such as the colour, just sort of like we're talking about with the radiator. Also things such as surface area, their temperature, and all of those things. So we will have a look at those, but of course they won't be in this test. Now, we certainly can look at this though. Why is it impossible for heat energy to transfer to the Earth from the sun via conduction or convection? Yeah, so you need to know, you've got 2 marks here, so you need certainly 2 points. So you can say that radiation requires no particles for heat transfer. So the fact that you're mentioning radiation, and we can say that conduction and convection require the transfer of particles. And we can also mention that radiation from the sun travels to Earth through the vacuum of space. It's really hard to write this quite neatly. So that's about all you would need. Probably didn't even need that much. Why is it impossible for heat energy? So if you're just talking that radiation requires no particles and that conduction and convection require the transfer of particles, that would probably be enough. Don't need to go overboard. Now, we've got a substance here, and what I'd like you to do is, Sophie, what's happening from A to B? So the temperature is decreasing. But what we'll say though, to be more specific, what would you consider that to be? A gas, a solid, a liquid? A gas, yes. So just say that. Can you just say, please, what state it's in? The gas is cooling. Gas is cooling would be enough. Now, from B to C, we've got a phase change. Whenever we have those horizontal lines, we have a phase change. Let me just do this. Actually, I think it's so we have a phase change. So we're going from a gas to a liquid. That should be enough. From C to D, it's now a liquid and it's cooling. Liquid is cooling. And from D to E, there's a phase change. And it's going from a liquid to a solid. And finally, E to F, we've got a solid is cooling. Nice. 5 marks there, probably. Yeah. Explain why the temperature of the substance does not change between B and C. And this is where I think in the electricity, where some of the explanations are a little bit vague. Some didn't get any marks, others some didn't even attempt it. But explain why the temperature does not change between points B and C. So what we can say is that the heat is, or because heat is energy. Okay, so the energy is used to break the bonds. And it requires quite, from a gas to change the state from a gas to a liquid. Okay, so that's really pretty much all you need for the 2 marks. Is mentioning that you're breaking the bonds and mentioning that it's changing state. You could also talk about that after the state changes, the temperature decreases in this case. Okay, we have a 1 kilogram metal object requires so many joules of energy. Just determine the heat capacity. So more of the same, really. So the mass is equal to 1. Q is equal to 2,510. And the change in temperature is 20. And we just want to find C. So if I wanted to find C, that's we just need 1 times C times 20. So we've got to divide both sides by 20, and then that will give us the heat capacity. So C is equal to 2,510 divided by 20. And that's going to give us 125.5. It's joules per kilogram per degree, or per degree Kelvin. Per degree Celsius. Okay, we haven't really done anything on state changes though. How many joules of heat energy are required to melt 25 grams of lead? So what we need to do is we need to look at when we're talking about melting, or we're talking about vaporization, we're talking about a change in state. So we need to use the energy, but this time we've got to use the mass times the latent heat of fusion for lead. Now they've told us that it's 25 grams, which is 25 grams is 0.0 because that would be 250 grams, 0.025 kilograms, and the latent heat of fusion for lead is 0.25 by 10 to the power of 5. Multiplying those out, that gives us 625 joules. How much heat energy must be transferred away from a 0.5 kilogram of ethanol vapor to change it completely to a liquid? So heat energy away must mean a cooling down. Heat energy in is a heating up. So we're looking at, once again, mass this time is 0.5. That's nice and easy. Now, we need to look at ethanol, and we need to look at the vaporization point of ethanol. So if we go up to the top, we will have ethanol. So we'll need to find ethanol on the table. So it says that the melting point is 78 degrees. So that's nice and easy then for us, because we don't need to consider the change in temperature and have two calculations. The latent heat of vaporization, though, is 8.7 by 10 to the power of 5. So we need to go ahead and use that. Okay, so we've got 8.7 by 10 to the power of 5. So the latent heat of fusion is 8.7 by 10 to the power of 5. So just multiplying those out, that's 4.35 by 10 to the power of 5. 10 to the power of 5 joules. Okay, we don't have much left. Actually, we've got only the one question remaining, and this is, generally speaking, this will generally be the hardest one for you guys to do. Is that all right? Okay, so what I'm going to do is I'm going to get you guys to have a go at this one. I'm going to pause this video. I think I can just do that by, where are we? So I'm going to pause. All right, so let's see how you went. I'm just going to press play now, and you should see my answer pop up there. So we had 4 calculations. The first calculation over here, this guy here, is for the heating up of the ice from -10 to 0 degrees at the point where it's going to change state. Not, as you can see, not a great deal of energy there, 4,200 joules. And make sure that you're using the heat capacity of ice to 2,100 and not the heat capacity of water as a liquid. And then we've got the melting of the ice, which is the latent heat of fusion multiplied by the mass, which is 66,800. And then we've got over here, we've got the heating up of water from 0 to 100 degrees is 84,000 joules. Notice that these changes of state use a pretty fair amount of energy, it's particularly when we're looking at the latent heat of vaporization, water going from a liquid to steam. You can see there that the latent heat of vaporization, 22.5 by 10 to the 5, and we multiply that out, that actually is probably about 3/4 of the energy involved. And when we add all of those up, I got 6.05 by 10. That's not 45,000, that's 450,000. That's 6.05 by 10 to the power of 5 joules. Now, something like this might be worth 5, even 6 marks. I think maybe we made this worth less just so if students didn't do it, they didn't lose as many marks. But it's probably fair to say that in your test, if you've got to do something like that, it might be worth, a solid 5 or 6 marks, at least 10% of your paper. So that's about it for me. I hope that I will record this, or I've recorded this, so we can go ahead and where is it? There we go. So I'm going to just stop this now.